Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. If you step on inside, guys, we are going to be working on perpendicular bisectors of triangles and angle bisectors of triangles, and the Circumcenter theorem and the Incenter theorem, Circumcenter, Incenter, theorems to solve some stuff. And at the very end, we're going to do some compass construction as well, if you'd like to stick around for the last problem. If not, you are totally good to go at that point. But let's go ahead and look at this problem set here, where we are going to be doing some stuff on the front on this perpendicular bisectors of triangles, and then the back will be angle bisectors of triangles. So let's start right here. This first one is less about perpendicular bisector of a triangle. Well, this is about the first set, problems 1 through 4, is about what's called the perpendicular bisector theorem, which is not going to be the same thing as what's really relating differently over here, with several perpendicular bisectors meeting at what's called a circumcenter right here. A little bit different. This one happens to have a triangle made as a result of trying to answer the question that's being done. So here we go. Given that line P is the perpendicular bisector of segment XZ and XY is 15.5, find ZY. So here's what's going on. It's already drawn, line P is already drawn, and it's drawn that it's perpendicular. It does not tell you yet that it is a bisector. I mean, it does not show it. So I'm going to go ahead and do that. A bisector is a line, ray, or segment that intersects a segment at its midpoint. And a midpoint is a point that's right in the middle of a segment that is equidistant from its two endpoints. So it creates congruent segments right here. So that's perpendicular bisector. Now the perpendicular bisector theorem states that any point on the perpendicular bisector of a segment is equidistant to those two endpoints of the segment. Not just point W, but also point Y. This point right here happens to be equidistant to X and Z, the two endpoints of the segment that is being perpendicularly bisected. So would it be another point right here if I called this point point V right there. You know, I could have called that. That would have been equidistant to X and Z. But we're on Y, and this is what we get to use. So I drew that up. Fantastic. XY is 15.5 units long. They want to find the length of ZY. Well, guess what? Its length is equal to XY's length. So it's also 15.5 units long. There we go. So that's number one. Now, number two, these are different values now, so we have to erase the 15.5 stuff. It's still a perpendicular bisector though, so I will go ahead and just erase that, and let's now look at number two. In number two, we have XZ is 38. Give me one moment. XZ is 38 units. YX is 27 units. Oh, I'm sorry. Hold on a second. These aren't given anymore. That's why they don't draw them. Okay. YX is 27 units and YZ is 27 units. Find ZW. Okay, here's what's going on. In number one, it was given that this line was the perpendicular bisector. In question two, it's given that it's perpendicular because the drawing, it does not tell you that it's a bisector anymore. So the perpendicular bisector theorem of when it's a perpendicular bisector like this, then it makes these equidistant, only applies if it's a bisector. If you don't know it to be a bisector, then it doesn't apply. Think about this drawing, for example. That is terrible. Think about this drawing, for example. These are perpendicular, right? Does that make this congruent to that? Of course not. It needs to be a bisector with it as well. We don't know that it is. What we do know is that these two segments are congruent to each other. These two segments have lengths that are equidistant to the endpoints of a segment from a point that is on a line that is perpendicular to that segment. This is the converse of the perpendicular bisector theorem, which states if a point is equidistant to endpoints of a segment, then it is on the perpendicular bisector of the segment. We already know that it's on a perpendicular intersection with it. That must mean, therefore, it is the bisector. I know I'm saying a lot of words. Sorry about that, but this is a must need to know. If this wasn't perpendicular, or if these weren't equidistant, then this part wouldn't have been able to be stated. So now we know that this is therefore a perpendicular bisector, they want us to find the length of ZW. ZW, its length, is exactly half that of all of the length of XZ. And XZ's length is 38 units. So ZW is half of 38, which is 19. ZW is 19 units in length. Okay, let's erase these because, again, the drawing does not tell you it's a perpendicular bisector, so I'm just going to go off this. Given that line P is the perpendicular bisector segment XZ, okay, we're back to that. XY is 4n units in length. Let's get rid of this as well. XY is 4n units in length, and YZ is 14 units in length. Find n. So it's the same thing as before. When the perpendicular bisector theorem, it'll make these two congruent right here. So I can set those two equal to each other to find n. You divide both sides by 4. You get 14 over 4, which can reduce to 7 over 2 if you end up writing it as a reduced improper fraction. That's my favorite answer. You could also put 3.5. I guess some people could put 3.5, but my preference is 7/2, personally. Okay, number 4, given that xy equals zy, so also that means that those two segments are congruent to each other. Looks like we're using the converse of the perpendicular bisector theorem again. So given those, then that means to us, guys, that these will therefore be congruent. Wx equals 6x minus 1, so right here. Xz equals 10x plus 16, that's the whole thing here. We got to find ZW, this little unknown. Now here's the thing. ZW and WX have the same length. They have congruent segments, right? So they have the same length. We're not just going to write 6x minus 1 right here. They really want us to solve for x, plug it into something to determine what it is. But it is true they have the same length, which means we can express it the same way. That's just not your final answer. Both of these can be represented as 6x minus 1 because they're equal. So if we add this with this, we should get the entire thing. That's the segment addition postulate at play. You could also just double it up. Just say if I double 6x minus 1, I'm getting 10x plus 16. So that's 12x minus 2 equals 10x plus 16. If you subtract 10x from both sides, you'll get 2x. Add 2 to both sides, you get 18. Divide both sides by 2, you get x equals 9. Now, that's solving for x, this unknown little bit right here. That's not solving for ZW. You got to substitute 9 into here. So ZW's length is going to be 6 times 9 minus 1. 54 minus 1 is 53. So ZW is 53 units in length. And there you have it. Okay, so that's the perpendicular bisector theorem at play. Not really involving a triangle. I mean, look, it has a triangle there because of what was given. But it's not the same thing that's going to be done right here. It sort of is. It's the crux of what's built here, where you have essentially 3 of those drawings together. Like, consider this single one here, where if this was perpendicular bisector, it's that part, therefore these. And then over here, you have the same thing. It's that part, therefore these. So you have those individual ones, but it's within a bigger triangle where all these points intersect right there. And I'll talk about that in a second. Use the figure for problems 5 and 6. Segments SV, TV, and UV are perpendicular bisectors of the sides of triangle PQR. Find each length. So here's what's going on. We do have perpendicular bisectors here, here, and here. They say perpendicular bisectors, so I can make markings there for that side. Let's say there for that side, and there for that side. By the perpendicular bisector theorem, we know, and I'm using a different color here, we know that it creates that equidistant bit, like, you know, right there. So these two are congruent to each other here. Well, from these two are congruent to each other, and because I already have a 4 tick mark thing, and I'm going to use that. And then because of these being perpendicular bisectors, these two are congruent to each other. So all 3 of these are congruent to each other, and that's really what this whole thing has to do with. It really has to do with the fact that from this point to my vertices, I have equal lengths. I have congruent segments. All these lengths right here are the same, which is really what they're going to be talking about. This thing right here is called a circumcenter. Now, I don't know if this thing is drawn to scale, but it's called a circumcenter because this becomes the center of a circle with a radius that's this length right here, whatever it is, VQ, RV, all that kind of stuff. It becomes the center of that circle, which means that circle is circumscribing this triangle. Yeah, that seems to work out. See how that circle hits that point, that point, that point right here? This is the circle's center. This is known as the circumcenter. All the perpendicular bisectors of any triangle always intersect at the circumcenter, which creates equidistant lengths to the vertices of your triangle. We don't need the circle, but we do need the circumcenter. So what is the length of RV? We know it's congruent to PV, and PV is 26 units in length. Therefore, RV is 26 units in length. What's the length of TR? TR, man, they don't have us do that much. I was waiting for Pythagorean theorem and stuff, but it looks like we're not doing it. What is the length of TR? TR is the perpendicular, TV is the perpendicular bisector of QR. These two parts are congruent. If TQ is 24, then TR is 24. So that was a lot of talk for doing very little work on this problem. I didn't even write any numbers here. But now you know kind of everything about that I guess you're supposed to know, and then some. Okay, numbers 7 and 8. Find the circumcenter of the triangle with the given vertices. Now I'll tell you what, this works a lot better with a graph, with like graph paper. So I'm going to go ahead and pop one up. I'm finding one on my computer. All right, one of my files here. So sorry if you don't get one here. This is to demonstrate for you what's going to go on, and I'm going to get rid of these later. But what we're going to do is the very same thing that you just heard before. This point, this circumcenter, is discovered by drawing perpendicular bisectors of your segments of your triangle. So that's what I'm going to do. I'm going to make a triangle. A is at 0, 0. B is at 0, 5. C is at 5, 0. And if we draw perpendicular bisectors of all these three sides of this triangle, they should all intersect at the same circumcenter. Now, 2 alone intersect at the circumcenter. So if it's hard to find a perpendicular bisector for C, we'll go ahead and just do them for A and B, and hopefully that should be enough. So, excuse me, not for A and B, for AC and B. Sorry, I said, If finding this one is harder to do for BC, then AC's perpendicular bisector and AB's perpendicular bisector should be easier. How come? Because counting horizontally or vertically alone is much easier than doing both. And we know that perpendicular to horizontal is vertical and perpendicular to vertical is horizontal. So what's the perpendicular bisector of AC? Well, if I count this distance of 5 units right here and take half that at 2.5, then this is going to be the midpoint of segment AC. And perpendicular to a midpoint, perpendicular to a horizontal line is a vertical line. So this is the perpendicular bisector of segment AC right here, this vertical line. Where does it intersect with segment AB's perpendicular bisector? Well, this is also 5 units up and down. Half of that is 2.5 away, and 2.5 away will be that midpoint. And perpendicular to a vertical line is a horizontal line, such as this one right here. So there is that guy's perpendicular bisector. Now these two should be intersecting at the circumcenter for this triangle, which is right here. Now this point is, by no coincidence, also the midpoint of segment BC. See, segment BC goes 5 units over, 5 units down, what have you. So half of that, 2.5 units over, 2.5 units down, gets you the midpoint. There are other ways to find midpoints. You average distances, things like that. I'm sure they might want you to think about it that way without a graph. That's why they probably don't have one, but I want to give you the visual. And if you wanted to draw a slope for a perpendicular bisector, it would be an opposite reciprocal slope, which means it would be going, instead of at up 1 over 1, it would be down 1 and left 1 like this. And this would have been its perpendicular bisector like that. Just draw like that. Sorry. Now, but there's no need to draw that line or find that midpoint because we already found the 2 points that intersect and it intersected on its midpoint. So there was no need to do it, but it's still there. It's still perpendicular to it. And the point is, this is still the circumcenter. This is still the center of a circle that's drawn that makes all those three distances equal from each other. See that circle that's drawn right there? Hold on, that kind of got messed up growing from the center. That circle right there makes this distance, and this distance all the same length. That's all that they're trying to come up with. Anyway, what did they want? They wanted the circumcenter right here. What is this location? It's 2.5 over, 2.5 up. 2.5, 2.5. There it is. A lot of work for that one. That's probably not needed. This one might need a little more work because it's not necessarily a right triangle. So let's take a look at what this second one here is doing. Number 8. D is at 0, 7. E is at -3, 1. And F is at +3, 1. Okay, well, it's an isosceles triangle, that's for sure. I don't think it's equilateral, but we'll find out. Let's draw a little skinnier things here. Now this one does require us to do a little bit more work because we have to come up with at least two of the perpendicular bisectors to find its circumcenter there. Let's start with the perpendicular bisector of EF. That should be the easiest one for us to do. So halfway in between these two is right at 0, 1 right here. And again, perpendicular to a horizontal line is a vertical line. So if I go ahead and start with drawing its perpendicular bisector, it'll look like that. So somewhere along the y-axis is the circumcenter of this thing. We got to find it. Let's take the midpoints of one of these, like for DF. So the way I'm going to do it, you can average your values, meaning add the x's divided by 2, add the y's divided by 2. But I'm going to use the visual that I have here. This goes over 3 units and down 6 units. So half of that, let's go 1.5 over like that, and 3 down like that. And we arrive at this point right here. The actual coordinate pair is it's 1.5, 4. But that part's not needed. What we do need to know is from that midpoint we have to draw a perpendicular line. If this slope was, again, down 6, right 3, down 6 over 3, that is a slope of -2. So its opposite reciprocal slope, there's that one. The opposite reciprocal slope, the perpendicular one, is -2 over 1, flip it over, change the sign, it's 1/2. So this slope can go up 1 over 2 like this, up 1 over 2 like this over and over, or down 1 left 2 like this, down 1 left 2 like this, and it just kind of keeps going in that direction there. Now I'm only going to do it for this one. I'm not going to do it for the other one. It's going to be very similar-esque. But this opposite reciprocal slope, this perpendicular bisector, would be going like this right here. Let's go ahead and put it in green like the other one and kind of get rid of all the other stuff. It's kind of a lot of work for that, right? But they do intersect at this thing's circumcenter right there. It's that point. Now this one's a little harder to kind of come up with what it is as far as talking about. Give me 1 second. Hold on. The actual location in itself is a little bit harder to talk about from a graphing standpoint because you'd have to know kind of the math as to what goes on with the slope. If I was going down 1 over 2 right here, then what happens in between is you go down 1/4 to go over 1/2, and 1/4 to go over 1/2, and 1/4 to go over 1/2. So you went down 3/4 from the original spot, so now you're up 1, 2, 3 1/4, 3.25 at 0, 3.25. That's a lot to kind of do. It's kind of hard to make sense of. It's not the easiest problem for people to do. The algebraic version that I would really want to think about is I'd probably write out the equation in point slope form, which still isn't much easier because it has a decimal. What did I say this thing was right here? This was 1.5, 4. So there's an equation I could write. Again, if this is over your head, then you just move on. This is y minus y1 equals m times x minus x1 right there. And this is equal. So that's that equation right there. So you could find a way to find out when this whole equation is set equal to the equation right here, x equals 0. So what you would do is you would substitute 0 in for x right there, and you'd solve for what y value it is, and you should get 3.25. Let's see if that works. You'd get y minus 4 equals 1/2 times 0 minus 1.5. Now 1/2, by the way, is 0.5. If we're going to be using decimals the whole way, we might as well. So 0.5 there. So y minus 4 equals 0.5 times negative 1.5. And you can see why I'm so not a fan of this now. Y minus 4 equals, that's negative 0.75. Add 4 to both sides, you get y equals 3.25. So when x is 0, y is 3.25. And you can see that right there, and that's what we get. So there's a lot of work for that one. It's definitely a much harder problem than on any of the other ones before it, but that is the circumcenter. And of course, that does mean that I could draw a circle that just expands out to those 3 equidistant parts, which are right here, and here, and here. It's kind of like the, isn't that like a Star Trek looking thing? I think it is. All right, so I'm going to get rid of those drawings there, but that was how those problems work. And this one might be a little more of the same. All right, use the graph of triangle ABC to complete problems 9 through 15. Yeah, kind of similar-esque. Draw a perpendicular bisector segment CB on the graph. No problem, because this is the horizontal one. 1, 2, 3, 4, 5, 6, 7, 8 away from each other. Halfway is 4 away, which is right there. Its perpendicular bisector will be vertical, as we just saw previously. Hopefully this is now making sense, at least on the vertical horizontal ones on the graph. So let's check that out. Boom, there's our perpendicular bisector. Now let's use the midpoint formula to determine the midpoint of AC. This time I'll actually do the midpoint formula with you guys. A's actual location is 7, 10. C's actual location is 1, 2. To find the midpoint for these things here, we have to average the x's, 7 plus 1 divided by 2, average the y's, 10 plus 2 divided by 2. Well, 7 plus 1 is 8, and 8 divided by 2 is 4. 10 plus 2 is 12, divided by 2 is 6. So 4, 6 ends up being this midpoint right there. That's kind of that, how I'd count that and count half of it and get there. So this is going to be 4, 6. By the way, I already checked that one off. What is the slope of segment AC? Well, AC's slope is you do a rise of, see, this is why I wanted to use this before, a rise of 8 and a run from 1 to 7, right? And a run of 6. So rise of 8 and a run of 6. I want to be sure that's good. Yes. So 8/6 or 4/3. What is the slope perpendicular to this? You take the opposite reciprocal. Change the sign, -3 and over 4. So what we're going to do, we're going to draw, oh, they tell us to do it number 14. We're going to use the point slope form to find an equation of the perpendicular bisector. 4, 6 is your x1, y1. Here's your slope, -3/4. So we're going to say y minus y1 equals m times x minus x1, like that. And we are going to now draw this guy's perpendicular bisector, which is using that slope of down 3 and right 4. So we're going to go from here, 1, 2, 3 down, 1, 2, 3, 4 over. About kind of there-ish. I'm going to go ahead and draw that one out, which looks about like that. And then they are meeting at the circumcenter for this thing right here, which doesn't seem to go right on an integer, despite how much you want to force it. It does not seem to be doing exactly that. It's probably 3/4 up from that point. Again, they're actually not asking us to find the circumcenter. They are just asking us what's it called. It's called the circumcenter. So that is that last part that we found there. And again, that circumcenter does create, right, if I expand a circle out, notice how A, B, and C are all on the circle itself because those are radii that are drawn. And that's, of course, what we were doing. And we could have done it for segment AB as well, but that's all we're going to talk about there. Okay, so that's it for the perpendicular bisector stuff. Let's now move on to the angle bisector stuff, which still involves some triangles and something involving circles, but in a different way. So going straight into it right here, angle bisectors of triangles, given that FG is equal to HG. So, sorry, let me, before I'm talking about that, what we're going to do Let's start with a simple concept of angle bisector, just for one part, and then dive into the triangle. So if this angle was to be bisected, if I were to draw an angle right here that divided this angle into two congruent parts right here, what's true about this is any point that's on the angle bisector is going to be equidistant to the two sides. I guess that doesn't really look like an angle bisector, does it? Let's do a little more like that. A point on the angle bisector is going to be equidistant to the two sides of the angle that's being bisected. So these two guys right here are going to be congruent to each other. Now the converse is also true. If a point in between, in the interior of an angle, is equidistant to two parts of your angle, to the two sides of your angle, then it is on the angle bisector. It is on the angle's bisector right there. So what they're showing you right here is they say FG is equal to HG. So these two are congruent to each other right here. And if you notice, ignoring everything up top, you're kind of looking at this angle right here. This point is equidistant to those. Therefore, it must be on this guy's bisector. These two must be congruent right there. I'm going to get rid of some of that marking stuff and just show that, yes, that would make this congruent to this. So measure of angle FEH is 55 degrees. That's the entire thing right here. The entire thing's 55. And they want to find the measure of angle GEH, just one of these right here. Well, it's true that we're on the angle. Oh, you can't see some of the stuff. I'm sorry. There we go. It's true that we're on the angle bisector right here. So this is going to be divided in half. The measure of angle GEH, I keep forgetting my pictures there whenever I'm talking to you guys. Measure of angle GEH is half the measure of angle FEH. FEH is 55 degrees. So the measure of angle GEH is half of 55, which is 27.5 degrees. Okay. All right, given that, let's do number 2. Erase that. Given that segment EG bisects angle FEH, what we just saw. So again, it's a bisect right here. And G, so that'll make this congruent to this here. GF is the square root of 2. Let's find GH. Well, it's going to be the square root of 2. That's all. All right. Given that angle FEG is congruent to angle GEH, so we're back to that again. So that must mean that because they're congruent, that GE is a bisector. FG is 10Z minus 30, and HG is 7Z plus 6. Find FG. So it's one of those things, again, let's solve for Z within the setup right here, knowing that these two are going to be congruent to each other by the angle bisector theorem there. So 10Z minus 30 equals 7Z plus 6. Subtract 7Z from both sides. Add 30 to both sides. Divide both sides by 3. Z is 12. We're going to use that 12 and substitute it. You technically can substitute it into either one because even though they're different expressions, they both represent the same length. But we'll just do it to 10Z minus 30. So FG is 10Z minus, 10 times 12 minus 30, which is 120 minus 30, or 90. This isn't 90 degrees. Don't just automatically put degrees here. It's 90 units in length. All right, last one. Given that GF equals GH, again, we'll use the converse of the bisector theorem here. Given that GF equals GH, measure of angle GEF is 8/3 a degrees right there, and measure of angle GEH is 24 degrees. These are bisected, by the way, because of that reason. Find A. So we can set these equal to each other. We can say that, 8/3 A equals 24. And then we can get A by itself by dividing both sides by 8/3. It's better by saying multiplying it by its reciprocal. Multiply both sides by 3/8 like that. I feel like I gotta sneeze. And so, yep. Excuse me. And so when you do, instead of doing 24 times 3, let's start with 24 divided by 8, which is 3. Times 3 is 9, so A is 9. There we go. And you don't have to put degrees because the degree symbol's already kind of represented with that on the A portion right there. And those are your 4 answers, straight into the angle bisector theorem. Okay, we continue on the angle bisector theorem here. Now, the theorem, excuse me, that was the angle bisector theorem. Now we're going to go into what's called the Incenter theorem, which now explores within a triangle, what if you had 3, or just 2, I guess in this case, but what if you had angle bisectors all around? And I will show you it in great detail. I know they have to cut it off, but I'm going to do this. All 3 angle bisectors of a triangle, meaning congruent angles here, congruent angles here, congruent angles here, all meet at a certain center. It's not the circumcenter this time. As you can tell, if I tried to draw a circle here to go around these, it clearly doesn't meet all 3 vertices. But this is what's known as the incenter. The incenter is specifically for a circle that inscribes your triangle, that when I draw a circle right here, it hits all 3 sides of the triangle like that in an equidistant manner. And a radius, oh gosh, how do I say this? A circle has the sides of a triangle at its shortest distance tangentially, meaning it hits it at just one spot. And the radius of a circle intersects with a tangent at 90 degrees. So these perpendicular distances to these sides are all congruent to each other. This is congruent to this, is congruent to that. Now it's the distances to the sides of the triangle, those perpendicular distances, that are equal to each other. And that's what the Incenter theorem states. So that's a lot of drawing stuff right there, and it has very much to do with the angle bisector stuff, because all those distances to those sides, see if this is an angle bisector right here, that would make these 2 distances congruent to each other, as we've kind of spoken about, right? So it's kind of the same things we talked about before, only instead of a circumcenter, all that kind of stuff, it's an incenter. Okay, so we are given that GJ is an angle bisector right here, so that will make these 2 congruent. We are given that IJ is a bisector, so that'll make these 2 here congruent. Now that does lead to, like I said, some other parts that are going to be, congruent and such. Find each measure. We're going to find the measure of angle JGK. So JGK is right here. If this guy is 23, then so is JGK. So also 23 degrees. Measure of angle JIK. Looks like JIH is 82.1 degrees. It's not really drawn to scale. Oh, no, I'm sorry. That's a length right there. That's not degrees. That's this length. The whole thing, I'm like, that's not really drawn to scale. That made me confused. The whole thing right here, we can find this measure by finding out this angle, knowing this angle, and taking them away from 180 degrees. So the measure of angle HGK in total is 23 times 2, or 46 degrees. So 46 and 26 can be subtracted from 180. So the measure of angle JIK plus the 46 plus the 26 is 180. The measure of angle JIK plus 72 equals 180. Subtract the 72, the measure of angle JIK is 108 degrees. So the whole thing's 108 degrees. I'm sorry, I said JIK. That is GIH. Let me say that one more time. I was saying the wrong thing. I'm talking about the entire angle. GIH. My bad. JIK will be half of that. So GIH, the entire thing, or KIH. GIH. So that's 108 degrees. So JIK will be half of the measure of angle GIH. Measure of angle JIK is 1/2 the measure of angle GIH. So that's 1/2 of 108 degrees, which is, I don't know if you can see it or not. I can't see myself in my own picture thing, that's why. Which is 54 degrees. That was a lot of work for that. So 54 degrees right there. So that is this guy. Okay. Find the measure of angle KJI. So KJI is right inside here. Knowing that this is 54, knowing that this is perpendicular here, that's 90 degrees. All three of these add to 180. Or better yet, and I don't know if I talked to my students about this right here, the two non-right angles of a right triangle are complementary to each other. Because if this one's 90 and they all add to 180, then take away the 90 right here and the rest, the other two add to 90. So the measure of angle KJI plus 54 degrees right there, we just found out that's 54, is 90 degrees, right? These two just add to 90, plus that 90 is 180. Subtract 54, so basically they're complementary. So the measure of angle KJI is 36 degrees right there. All right, there we go. All right, let's find the distance from J to GH. So J to GH, when they say distance, they mean perpendicular distance, the shortest distance to there. And like I said, the incenter is equidistant to each side of the triangle. So this is equal to this right here. And if this is 64.3 units in length, then so is J to GH. It is also 64.3 units in length. And lastly, the distance from J to IH should be the exact same as the incenter theorem states from before. So that is also going to be 64.3 units in length. Apparently you never needed the 82.1, so that's good. We're done. Almost a decoy there. One more question here. Now, if you are not using compass construction, this is a good time for you to stop. If you don't have a compass in front of you, if you don't want to observe. I will say though, you know what? I'll do it in a rough sketch way, and then I'll use the compass version. I don't know if it's going to go very well because I have to use a tool on this computer thing that I haven't used in years, and I got to make sure I even know where to find it on here. So it might. Oh, I think I know where to find it. I got to know how to use it right. Okay, so let's look at the problem. Whether or not you're using compass, let's look at this problem here. Raleigh designs the interiors of cars. The triangular surface shown in the figure is molded into the driver's side door as an armrest. Raleigh thinks he can fit a cup holder into the triangle, but he'll have to put the largest possible circle into the triangle. So basically, there's a cup holder in this portion of the door inside the interior here. He wants to make a circular cup holder. He wants to make the largest possible one, which means one that's going to fit as the in circle of the triangle. So explain how Raleigh can sketch his design on the figure. And you know what? I'm not sure if they actually want to use compass construction, but for us, the explanation will be Raleigh should construct an incenter. So let me start here. Raleigh should construct an incenter of the triangle. So the incenter will inscribe the sides, right? It'll scrape right against each side of the triangle right there, which means, excuse me, so if he, constructs, hold on, so he should create, so if he constructs angle bisectors of each vertex of the triangle, he should create an in-circle. I'm sorry about this. He should construct, and that's a word. He should construct an incenter, or they should intersect at an incenter. You can tell I didn't do this one yet. They should intersect at an incenter, and he can make perpendicular perpendicular lines to each side of the triangle. All right, so this might take a while for me to construct because some of these things, honestly, I don't know if I remember how to do all the constructions for these. Okay, so that's kind of what we're going to do there. So a rough sketch version will basically be this. If we did an angle bisector of that angle, an angle bisector of that angle, and an angle bisector of that angle, and technically you only need two of the three, right? But they would all intersect at one point. that one point, now remember, that would create an incenter, which means the circle should be able to inscribe those three sides of the triangle. Clearly, this wasn't drawn to scale, otherwise it would have been done perfectly. But it should kind of look like that. That's the kind of thing he wants to make. Now, in order for him to make that circle here still, we have to figure out what points of the circle it's going to touch the sides. So you then have to create perpendicular lines to there and there and there on this thing, so that your circle can then be made with it. And honestly, you might only need one. Well, actually, with a compass, you don't need any perpendicular parts. You just need to get to one of them, and then once you start drawing the compass, it should go all around. So, okay, maybe a little less work than that. So what I'm going to do, I'm going to use compass construction, but I'm only going to do it with two of the angle bisectors. So I'm going to make two angle bisectors. I'm going to make one here and here. They're going to intersect at the incenter. I don't need to make the third. And then I'm just going to use the compass and reach out this point, and then I'll draw the circle with the compass on that thing. Perfect. I don't need to do any more than that than I have to. So how do you draw? Here's my compass. Wait, was it made? Hold on, it might be up top. There it is. Here's my compass. I got to bring it down. So how do can I change the size of the compass itself? I don't think so. Okay, how do I use this tool? I'm sorry about this. I do not remember how this, here we go. Okay, so how do you use a compass here? I'm not going to explain compass stuff too much, except for like what a compass does, whatever. So, well, I mean, what it does, you can draw, so you can draw some things like that, and you can actually at home as well. Okay, so with this compass here, how do I change the pen size? I'm sorry, I got to remember how to do all this. What's that, 81? I know I can change the pen size somehow. Is it with... Oh, I can change the pen color. Perfect. Okay, I'm going to use that size and that color. Okay, so here we go. So what you're going to do here is you are going to draw two arcs that need to be the same distance away from your vertex you're then pivoting. So I'm going to draw an arc right there, and over here on this side I'm going to draw an arc right here. From here, I need to now place my pivot on each of these arcs. I can make a new length if I'd like to, and as far out as I'd like to as well. Let's see if that's rotating along it. Yeah, I can go over a little more. One more. I can change the arc length here if I'd like to. It doesn't let me land on it. That's weird. Okay. I can change the arc length to anything I like to, but I got to stick to this arc length here. And I'm going to draw it outward right here on this one. And no, keep the length. And then over here on this one, I'm going to do the same thing, and I'm going to intersect those two. Where those two intersect is a point that is on the angle bisector because of this equidistance thing that I did right here. So from this point, oh, got to kind of get rid of the compass for a second. How do I delete it? There we go. Oh, man. Okay. I don't seem to have my marker tool anymore. But from this point to this point, I'm going to draw a line. That line will be an angle bisector for this entire thing. So that will be, I'll do that in blue as well. So this is the angle bisector for that angle right here. This is as exact as I can get for 45 degrees, pretty much. I say 45 degrees because this looks like it's a 90-degree angle. Pretty much. All right, there's my angle bisector. I'm going to do the same thing for this other one. So I'm going to make one more. I'm almost done. So for this angle up here, I'm going to do the same thing. I'm going to make two arcs. Let's use a different color. Make an arc right here and an arc right here that are both equidistant, and from here I can change out the distance and meet my pivot at those arc marks that I made. You following along with your compasses? I'm going to make this a little farther out, apparently. Build an arc there and just make sure this other arc can intersect with it on this one here. I can't seem to land right on it. That'll have to be close enough. So where that intersects right there, boom. There we go. Okay. So I can now draw another line. that's going to come from here out to where that intersects right there. That is the angle bisector of that angle. So where these two lines intersected is the incenter right there. There we go. Now I can make all these kind of faint. I'd like to make them a little bit faint. There we go. Kind of makes it a little easier to see what's going on there. Even fainter for those two. But that's all my scratch work for that. Okay, now to draw the circle itself, you just use your compass. Remember, all these should be equidistant. All I got to do is find the right length that'll match up to any one of these sides. Like, say, that one right there. Oh, that doesn't get perfect. Doesn't look like I'll be able to get perfect with the size. Oh, man. Okay, this doesn't get perfect. Oh, you know what? You know what? That's good enough. We'll just go ahead and say that it was like that. And that circle there. Huh. Okay, I guess the pivot's not right at the right spot. It's just a little underneath. Let's try that again. That circle right there gets essentially what was supposed to be the perfect incenter. So, as you can tell, I have pixel problems with mine. You know, pixelation problems with mine because it's just not big enough of a triangle for it to do it. But that's what's going to do it right there. And Raleigh has now designed it. It's a lot easier to do with a pencil and something that's a lot bigger with an actual pencil and come something that's a lot bigger. All right, guys, that was the last one there. Hope you enjoyed it. All right, so that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching, and I hope it was a little bit fun. I will see you in the next one. Take care.